I am Nikhil, and I'm one of the senior software engineers in Arm's machine learning team. My team and me try to optimize and enable machine learning workloads for Arm Neoverse platform. Today, I'm going to show you how we are supercharging generative AI on Arm Neoverse using KleidiAI and PyTorch. Talking a bit about Arm Neoverse and how it can power GenAI at scale, right? We can talk about what is Arm Neoverse. So Arm Neoverse is a family of 64-bit ARM CPU cores and compute subsystem, which is designed to for cloud ARM servers and infrastructure applications. Couple of features of Arm Neoverse. The latest generation of Arm Neoverse V2 is based on Arm v9 platform. It has scalable vector extension 2 support, which unlocks massive data level parallelism. It has massive compute capabilities and hardware acceleration for AI and HPC. Another big advantage of Arm Neoverse is its widespread adoption in major hyperscalers like AWS, Microsoft Azure, Google Cloud, and many more. Right, so Arm Neoverse can help speeding up inferencing at scale. From this slide, you can see that inferencing is approximately 80% of the ML workload. Once an ML model is trained, it spends close to 80% of its lifetime, answering user requests rather than learning again. So training is just the tip of the iceberg, where GPU comes in the picture, and it's just 15 to 20% of the total AI workload. All the real-world AI applications, such as natural language processing, automatic speech recognition, object detection, recommended systems, image generations, are very inference-heavy. But inferencing all these applications at scale come with its own challenges, and it's not trivial to run on CPUs. Couple of challenges we have listed over here. To run those applications on CPUs, we face memory bottlenecks, limited parallelism, and because GenAI models are much larger in size, we also have to take care how we scale these models across CPU cores and nodes. So what does the solution demand? The solution demands a fast and memory efficient and optimized solution, which is highly tailored towards CPU, and it's scalable, and it should be simple as well, so that everyone can adopt it and use it. With this being said, we can define that 3 major pillars to supercharge GenAI at scale includes efficiency, scalability, and simplicity. We're going to look at the first one, efficiency and performance, right? So for supercharging GenAI workloads, we would like to do the same amount of maths, but we like to do it in lower bits. And ultra low bit quantization can be a great enabler for that. Talking about ultra low bit quantization, we try to convert our floating point full precision model to a smaller format Int4. We directly performs the computation in quantized form. It gives you leverage in terms of 8x higher data density, higher effective memory bandwidth as more data can move per cycle. Specifically for Arm Neoverse, the solution can leverage Arm low-bit instructions like i8mm dot products, enabling 120 to 128 max cycles and 64 max cycles respectively for the instructions, and it significantly boosts integer maximal throughput, which is the major bottleneck in the GenAI workloads. This sort of quantization can achieve near original accuracy on large language models. We have presented the accuracy metric over here. It is being cut off from the screen. But as you can see on the screen from this diagram, we have an FP32 tensor, and we are applying a quantization, an apps-max quantization to Int4 on this. And what we get after that is a smaller compressed matrix along with some scaling factors, so that we can inflate the integers which you get out after the quantization and use them appropriately in your matrix multiplications. Moving to the second pillar, scalability. We would like our solution to be scalable. When I say scalable, it should be scalable across model types. Whatever new models you are seeing these days, it should apply to that. It should also scale with newer platforms, newer architectures. So the obvious choice is to integrate our solution with a leading ML framework like PyTorch. On the left side, you can see the current paths in PyTorch that are there for Arm Neoverse platforms. On the top, you have all the image generation, object detection, LLM recommended workloads. They're being offloaded to PyTorch. PyTorch internally has a tensor library named as A10. This library directly connects to your hardware using a couple of different routes. One of them is a third-party open source route like OpenBlast. Another one is 1DNN, which is a widely popular framework for CPU vendors. 1DNN internally connects with Arm Compute Library, and all these paths leverage the hardware features of Arm Neoverse. So what does this integration offer to us? It ensures seamless adoption and ease of use. Once you integrate a solution with PyTorch, it's distributed from Raspberry Pis to Arm Neoverse and everything in between. PyTorch is the leading training framework for GenAI models, which also means that you get day zero compatibility with any new model that are newly launched. We'll talk about the last pillar, that is simplicity, a bit later. But let's see what are the building blocks of the solution and how we can leverage KleidiAI, which Felix talked about, in PyTorch and accelerate GenAI workloads on Arm Neoverse. Some introduction on KleidiAI. KleidiAI is a highly efficient microkernel library designed to accelerate your AI workloads. What sort of things it offers? It offers optimized AI microkernels, provide low-level, highly optimized microkernels designed for Arm CPUs, quantized maternal kernels, especially designed for GenAI use cases. It also offers fast packing routines. It offers kernels which can rearrange your data to be more memory efficient. And the biggest advantage is KleidiAI is independent and stateless. So you can just take parts of KleidiAI, plug it in your ML frameworks. It does not hold any state. So it's a very big advantage. What sort of users we are targeting with KleidiAI? We're targeting AI framework developers, SDK developers, AI pipeline developers for all their classic ML, GenAI, and agentic AI workloads. Now we're going to have a comparison between KleidiAI 4-bit maternal kernel, which we have integrated in PyTorch, versus an already existing float32 kernel to accelerate maternals. Why specifically maternals? Because maternals have, if you profile any large language model, you would see that maternals are like 95% of the total workload in that model. So it's good to optimize the hotspot first. On the right, you can see we have a floating point 32 maternal, which takes an FP32 weight. It takes FP32 input, runs FMLA instructions on Arm Neoverse and gives you an FP32 output after doing a maternal operation on it. On the other side, you can see there's a KleidiAI 4-bit kernel, right? In the very middle, you have a microkernel, which is internally using i8, mm, and .word instructions. It takes input in int8 called quantized format, along with FP32 scales that we saw a couple of slides back. For the weights, it takes int4 quantized weights along with FP32 weight scales. All this data is fed into the KleidiAI microkernel that you see in the yellow in the middle. The maternal computation is performed in the lower bit using i8, mm, and .word instructions. The result is dequantized using the FP32 input scales and FP32 weight scales. And the output, you get it, and because it's dequantized, you get the output in FP32 format. So we have talked about how int4 can accelerate your GenAI workloads, why int4 is good for LLMs and all these large language models. But we still haven't answered one practical question. how do you reach from a floating point 32 ordinary weight and floating point 32 input to a data type that KleidiAI can understand? In this case, int4 for weights and int8 for inputs. Well, KleidiAI also offers you a couple of more kernels, which we talked about before, which is the packing routines. Before going to that, KleidiAI offers you to bring your own int4 quantizer. You can bring your own quantization scheme, and you can quantize your weights using your own quantizer. You can control accuracy better. If you want to experiment with numerous type of 4-bit quantization schemes, you can do that. Once you are satisfied with the your weight quantization, you can feed it to KleidiAI RHS scale and pack kernels. So RHS is just a convention we are using for weights, and LHS is another convention we are using for input over here. Once you do that, KleidiAI packs your quantized weights and scales into one single buffer. That buffer is represented on the diagram over there. For the input, we try to quantize them and pack them on the fly inline. Usually in an ML model, the weight is much larger compared to the input, and it's pretty efficient to pack the smaller data on the fly. It also helps in maintaining the accuracy of your model. So this particular kernel try to quantize your input as well as pack it, and this is offered by KleidiAI. Once you do these two operations, you can feed it to your matmul, and the output you get is the same output in terms of data type as your float 32 matmul. This makes this operation directly pluggable and replaceable in your ML model. So we're going to talk about what are the different stages of performing these two packing and quantizing operations. For the first one, on the weights, we try to statically quantize these weights during model loading time. And this needs to be done only once. Usually with any ML model, you have these weights available to you already. What is not available to you already is the input, which is always dynamic. So KleidiAI offers you this kernel, which we just talked about. You will quantize and pack this input on the fly dynamically to maintain accuracy. We have the packing routines from KleidiAI. We have the matmul routines from KleidiAI. So we take it and plug it in PyTorch. Over here, what we have done is integrated a new path, which is called Arm KleidiAI path into PyTorch 810 library. I hope you guys remember this diagram from a couple of slides before, where we just had OpenBlast and 1DNN path, but now we have Arm KleidiAI path. It can directly talk to the hardware. All these workloads can be offloaded to PyTorch. So what we have done over here is we have written a small wrapper over KleidiAI and integrated that wrapper along with KleidiAI in PyTorch. This wrapper helps you choose the best performing kernel from KleidiAI for 4-bit quantization technique. We have exposed this wrapper in terms of two user-facing 810 ops. These ops can be directly used by the user or consumed by the user. One of them is, of course, the packing routine, which is dynamic quant pack 4-bit weight, and another is dynamic quant matmul 4-bit. This op helps you in packing your weight data, and this op helps you in doing the matmul on your pack data. The third pillar, which we talked about, is the simplicity. And we want our solution to be simple and widely accessible to all the users. And we would also like to offer something which can just work out of the box. So we try to make quantization effortless. And here comes the TorchAO. TorchAO just is a supporting tooling library for PyTorch, which helps you inference your models in all sort of different bits and precisions. One of them is 4-bit. So in the code snippet, you can see with just one API call, you can quantize any PyTorch model. You can load any Hugging Face model, any PyTorch model, and you can pass it to this quantize API, and it would be quantized in place, ready to be accelerated by KleidiAI. Couple of advantages over here, just one API call. Seamlessly integrated with PyTorch and KleidiAI. TorchAO, with this sort of integration, gives you very fine-grained granularity over controlling the accuracy of a model. When I say controlling accuracy, I mean you can control what would the group size for the quantization, how accurate the quantization would be, And it also gives you control over choosing which layer to quantize and which layer to keep in unquantized format. So third-party developers can directly use this API along with PyTorch and accelerate their models using KleidiAI via PyTorch. Here's a full-fledged diagram or flow, what happens to a PyTorch model when it goes through TorchAO. So here you can see we have a original PyTorch model in FP32 precision. I'm highlighting one matmul layer in the model, which has floating point 32 weights. We feed it to TorchAO, and we run a couple of passes on this model. The first pass is quantize your weights, right? KleidiAI offers you row-wise and group-wise quantizations, and you can run these passes. Your weights would be quantized and stored in memory. After you have quantized your weights, it's time to replace your floating point 32 matmul layer with a KleidiAI optimized layer, which is also already being taken care by TorchAO. Once you have replaced your matmul operations, right, you would replace the FP32 weights that you have quantized over here in the model itself. And on the other side, you can see the model has been transformed, and now it's being accelerated by PyTorch and KleidiAI. It's using a KleidiAI info matmul along with the packed weights. The advantage is that the output data type remains same. So KleidiAI matmuls are like plug-in, info matmuls are like plug-in replacement for FP32 matmuls in any PyTorch model. This was supposed to be a video comparison, but it's a PDF presentation. But you can see, we are running a Llama 3.18b model in FP32 precision, and over there we're running a Llama 3.18b model in 4 precision. This model is still thinking. The prompt that we have sent to this model is still being ingested, and it has not started generating anything. While on the other side, you can see the KleidiAI model has already thought on the prompt, ingested it, and started generating, and it's already halfway through. You can see the performance comparison over here. The Llama 3.18b model is doing 13 tokens per second, and the info model is doing 68 tokens per second. It is being run on AWS Graviton 4 C8G instance with 32 threads using PyTorch compile mode on PyTorch version 2.7. Couple of benchmarking and performance data and what sort of impact we managed to create with KleidiAI integration in PyTorch. So we benchmarked Llama 3.18b, Gemma 2.2b, Qwen 2.5 14b on Arm Neoverse platform. All these LLMs operate in 2 different phases. One of them is prompt prefill stage, and another one is text generation phase. In the first phase, whatever query you send to these LLMs is being ingested, and the LLM understands the context around your query, and it takes some time. It does all the matmul operations. In the next text generation phase, once it has thought over the prompt, it would start generating the output. Right? So on the prefill stage, which determines how fast you get your first output, we managed to get a 4.2x speed up on Llama 3.18b model, going from 142 tokens per second to 606 tokens per second. On Gemma 2.2b model, we went from 270 to 110 tokens per second. And a similar story for Qwen 2.5b 14 billion parameter model. In the text generation phase, which is what we usually care about. Nobody wants to wait for their LLM to generate text. Llama 3.18b model goes from 13 to 68 tokens per second, Gemma 28 to 110 tokens per second, and Qwen 2.5 14b model goes from 9 to 37 tokens per second. And all this is well above the human reading speed. Couple of key takeaways. Inference drives the cost. 80% of real AI workloads happen after training. Optimizing it moves the needle, of course, as we have seen in previous slides. Arm Neoverse is everywhere. It is widely adopted. SV2 gives a ready platform for CPU inference at scale. With help of N4 quantization, we can maintain almost original accuracy and also get 4 to 5x throughput. Because we have integrated a solution into widespread and very popular ML framework like PyTorch, and the tooling around it gives zero friction for any third-party developers. They can just use one API call from TorchAO and they can accelerate any model out of the box using KleidiAI and PyTorch. Proven results, as you have seen from the results in the previous slide, up to 5x faster token generation on a couple of these LLMs. We also managed to accelerate whisper models, stable diffusion models, and all sort of popular LLMs that are coming out these days. Resources and references, you can refer to Arm's community blog, learning paths, KleidiAI. You can scan the QR and get to know more about KleidiAI. Yep, that's about it. Any questions?
Is the KleidiAI open source? Code is open source or not?
Yes, it is open source.
It's open source, so I can go through all the source code about the calculations of this the microkernel implementation in the open source hub.
Yes, you can. Yes.
Okay,
yep. So you can just scan this QR code or go to KleidiAI GitLab repo, and you would see all the code over there. Yeah.
So I have another question. That I do not see you mention any about the multi-thread implemented in KleidiAI. Do you have any slides or any idea about how to use the microkernel to do these calculations over microkernel?
Yes. So I don't think I have the slides, but KleidiAI gives you examples, and it tells you what sort of kernels to use and what sort of microkernels to combine together to accelerate your workload, and it's provided in KleidiAI repo itself.
KleidiAI is mainly for the CPU, right?
Yes. Okay. It is specifically fine-tuned for ARM CPUs.
So, do you have any plans about that? That is in many systems we maybe have as multiple components that work together to do some calculations. So I do not know that for ARM or for a next step, it better has some plan or solutions. So this means that is we have the CPU, GPU, NPU in the same places. So we will do some applications. We will want the users use the same APIs to do the calculations, but it can distribute all the calculations between every component of these systems. So I do not know whether you have any plans to develop KleidiAI for these interactions.
Right. For now, KleidiAI is just limited to CPU. Okay. It does not provide you a heterogeneous way to exploit all your accelerators on the device. Okay, that's it. Thank you very much.